In this video, I'm going to show you how you can use the Cayley-Hamilton theorem to find inverses. So here's that matrix we were looking at in the last video. Here's its characteristic equation. Replace lambda with m and we get m squared minus 5m minus 6 times the identity equals 0. Now here's the very, very clever bit. Bring that identity part over to the other side, 6i. Factorize out one of the m's from this, m times m minus 5i. You need that I there because 5 on its own is a number, 5i is 5 times the identity. Okay, we're almost there. What we have, let's just actually neaten this up perfectly. I'm going to have I here, and I'm going to multiply both sides by 1/6. And I'm going to write it in a slightly weird way. I'm going to write m times m minus 5i times 1/6. Why is this interesting? Well, I've got m multiplied by a thing equals the identity. Well, if m multiplied by a thing is the identity, then that thing is the inverse of m. And that's the clever way we can find inverses using the Cayley-Hamilton theorem. I know for a 2x2 matrix, it's easy to find the inverse without doing this, but just wait until we get onto bigger matrices. So supposedly 1/6 of m minus 5i is the inverse of m. Let's check. What is this? Well, m minus 5i, that's let's see, that's 4 minus 5 is minus 1, 2 minus 0, 5 minus 0, 1 minus 5 is minus 4. Is that the inverse? Well, let's see. How would we find the inverse normally? Well, we'd say the inverse is 1 over the determinant. The determinant is 4 minus 10, so that's minus 6, so minus 1 over 6. And normally what we'd do is we'd swap these round, so 1, 4, we'd make these two negative, so minus 2, minus 5. And lo and behold, these are the same, because if I bring that negative inside, I've got 1/6 of minus 1, 2, 5, minus 4. And so it works. So it's really, really, really clever. In the 2x2 case, it's definitely not faster than finding inverses the normal way, but with 3x3s, it is. And let's have a go using this matrix here. So use the Cayley-Hamilton theorem to find m inverse. So first we need the characteristic equation. So 1 minus lambda, or the determinant of this matrix. And since we've got all those zeros, this is not going to be too difficult to compute. So 1 minus lambda multiplied by the determinant of this, which is 2, minus 3 minus lambda, forgot that. This one times this one minus 0. So we just get 2 minus lambda and minus 3 minus lambda. Then it's minus 2 times 0 times 0 and minus 1 times 0 minus 0. So it's that. Okay, let's expand this out and then convert it into m's to find the inverse. So expanding this one at a time, that first bracket I get 2 minus 3 lambda plus lambda squared, and then minus 3 minus lambda equals 0. You know what, I'm going to make that plus 3 plus lambda because I can just multiply through by minus 1, that's fine, giving me lambda cubed, 3 lambda squared minus 3 lambda squared is 0 lambda squared. Then what is that? Minus 9 lambda plus 2 lambda, that's minus 7 lambda, and plus 6 equals 0. Now, by the Cayley-Hamilton theorem, this implies that m cubed minus 7m plus 6 times the identity is equal to 0. So, factorising out an m gives me m squared minus 7 times the identity equals minus 6 times I. So to get that I on its own over here, I just need to be timesing this by minus 1/6. So that is m times minus a sixth m squared minus 7i. And this here should be m inverse, right? Because m times thing is identity, that thing is m inverse. So what do I need to compute? I need to compute m squared minus 7i and then times it all by minus a sixth, and that should be the inverse. So first job is work out m squared. So hack through m squared and we get 1 plus 0 plus 0 and so on. Multiply this all out, you don't need to watch me do it. So there's m squared, and now we just need to do minus 1/6 of m squared, which is this minus 7 times identity. So this minus 7 minus 6, and then 6 and 10, they stay the same, and then 0, and then this minus 7 is minus 3, and minus 4 stays the same, and 0 and 0, and then 9 minus 7 is 2. And that is the inverse, and we're done. And of course, you can neaten this up if you like, so we can bring in that minus 1/6 to get 1 minus 1 minus 5/3, and so on. 0, half, 2/3, and 0, 0, minus a third, but you don't really need to. So there it is. That's this very, very clever way of finding inverses without hacking through the usual algorithm that we use. All we actually had to do, the hardest bit, was squaring the matrix M, which is, yes, it's hard, but it's not as hard as finding an inverse the full way. Here's another one to try. If you think you've got the process, pause the video and try this one for yourself. All right, step 1, find the characteristic equation. So we're going to find the determinant of this. And what does that get us? It gets us 2 minus lambda multiplied by the determinant of that minus that. That 0 is useful because it means it's just 4 minus lambda, 5 minus lambda. Then minus 2 times the determinant of this submatrix, which is minus 2 times that stuff, minus 0. So minus 2 times 5 is minus 10. Minus 2 times minus lambda is 2 lambda. Then it's plus 1 times the determinant of this submatrix. So that is minus 4 minus that times that. So that's minus 16 plus 4 lambda. Okay, bit of a mess here, but it's fine. I'm not going to bore you with watching me expand all of these brackets, but concentrate and you can do it too. We get to this cubic equation here. There's the characteristic equation, and here's the CayleyHamilton theorem. M cubed minus 11m squared plus 38m minus 40i is equal to 0. Factorize out an m, and we get m squared minus 11m plus 38 times the identity should equal 40 times the identity. That means that m squared minus 11m plus 38i divided by 40 should be the inverse of m. And sure, it's a little bit messy, but let's do it. We're going to need m squared. Okay, so again, I'm not going to make you watch me hack through this expansion, but there we go, that's m squared. And we have to just put this all together now. So we've got 1/40th of m squared minus 11m plus 38 times the identity. And there's our inverse, which of course we could tidy up by bringing the 40 inside if we wanted. Okay, so that's the CayleyHamilton theorem. Super useful, and this clever technique for expressing the inverse in terms of multiples and sums of your original matrix. Okay, that's all on the CayleyHamilton theorem for now. See you in the next video.